the material modeling is the most crucial step. Because workpiece material can be metal, can be alloy, can be ceramic, polymer, composites, or any other material. One should know on which material I am going to build a model for machining. Our scope is not to explore all these materials, but mostly metal or alloy machining, because the constitutive behavior that I will choose for the metals and alloys may not be appropriate for ceramics, polymers, composites. They have different material models. So whatever I am explaining here, these constitutive or material models are suitable for metallic material or alloys. Okay, that is about workpiece material. Also define whether tool material you are going to take it as a deformable or rigid. Because if you are not interested in tool wear or something, the deformation of tool, it is appropriate assumption tool can be considered as rigid, because in conventional machining, already explained you, it is essentially at least 1.5 to 2 times harder than the workpiece. Or even the new cutting tool materials of like carbide and ceramic, they are very hard compared to your workpiece material of aluminum or mild steel, copper. Your cutting tool are very hard materials. So we will not lose any accuracy if we consider it as a rigid, mechanically rigid. If you want to analyze temperature distribution in it, it's fine. We can still assume it as a rigid, provide thermal properties, we can analyze its temperature. But if we want to model tool wear itself in finite element analysis, that time we cannot consider tool material as a rigid. We have to consider it as a deformable tool, apply appropriate wear law. You have to model wear using some of the famous wear models, and then consider it as a deformable and model it. But if you are not interested in tool wear, better to consider it as a rigid. It will save your computational time without losing any accuracy. Then, as I earlier stated, our main focus will be metallic material. We will talk more on metallic material modeling only. So we know essentially the metals are assumed to be homogeneous and isotropic. They show elastic plastic behavior. After elasticity, material go in plastic deformation zone, that is called as permanent deformation. And after that, there will be a local fracture appear and cutting will process. So basically, metal cutting involves all the rigorous material behavior into consideration. Means in your simple beam problem or bar problem, we never go beyond elasticity. That is enough for our analysis. But machining, there will be elasticity, then there will be plasticity. After plasticity, there will be a damage initiation, then local damage propagation, and then chip formation. So, material behavior we need to dig out. So, it starts with elastic behavior. So, the stress strain relationship for, let's say, linear elastic, isotropic, and homogeneous material, we can write by using 3D Hooke's law. So in 1D, everybody knows sigma equal to A into epsilon. So, but if you are modeling it as a 3D process, all 6 components of stresses will be involved. They are related with all 6 components of strains with 2 material properties. One is Young's modulus, other is Poisson's ratio. So 2 material properties are enough to get even a 3D state of stress for metallic material. So basically sigma denote, or sigma ij denotes stress tensor, epsilon ij denotes strain tensor, and they are related with the two material properties, E Young's modulus and nu Poisson ratio.